So first, let's take a look at Part A. Part A, for our experimental setup, what we're going to be doing is we're going to have some volume of hydrochloric acid and some volume of sodium hydroxide. We're going to add both of these to our calorimeter. Okay, it's going to heat up inside of there as they mix together, and it's going to be completely insulated, and we're going to be able to measure that temperature as it rises. We're given in our data the volume of the hydrochloric acid, the volume of the sodium hydroxide, the temperature of the final solution when it's all mixed together in there, and the initial temperature of the HCl. We're going to make the assumption that the initial temperature of the HCl is also the same as the initial temperature of the sodium hydroxide. It's pretty reasonable. If they were next to each other in the lab, you could assume that. First thing it's going to ask you is the temperature difference. So the temperature difference is always going to be the final temperature minus the initial temperature. So in this case, the final temperature is when they're mixed together, so T solution, and the initial temperature is the initial temperature of the HCl, THCl. The next thing it asks you about is the calories or the heat that's released, and we're going to call that Q, okay? And Q is going to be equal to the mass, the total mass of the system, times the specific heat capacity, times the delta T. The mass here is going to be the mass of the HCl plus the mass of the sodium hydroxide. But we weren't given those. We were only given their volumes. So what we're going to have to do is add those two volumes together and then multiply it by the density, which I used a Greek letter rho here for. We're making this easy on ourselves, so we're going to assume that the density here is the same as water, and it's just simply 1 gram per milliliter. Then we're going to multiply by the specific heat capacity for water, 1 calorie per gram per degree Celsius, and then we just multiply by the delta T that we found up here. After that, we need to figure out the moles of acid that we neutralize in this process. So that's going to be the concentration of the acid times the volume of the acid. The concentration of the acid is 1.00 molar HCl. That was in the experimental PDF when we for the experiment. Don't forget to convert the volume to liters. This volume here is going to have to be in liters, so that when you multiply it by molarity, you get out moles. Okay. The last thing it's going to ask us for is the calories per mole. And that's just going to be the Q value that we have up here divided by the moles that we calculated here.
Part B is going to be very similar to Part A, only this time we're going to be taking an ionic salt, adding it to the calorimeter when we're going to be mixing in a certain amount of DiH2O. As the salt dissolves in the water, it's going to cause the temperature inside of the calorimeter to either go up or down. For our provisional data, we're going to be given the mass of the salt, the temperature of the water initially, the volume of water that we're going to be used, and the final temperature of the salt water mix inside of the calorimeter. In order to calculate the change in temperature, we're going to be using the final temperature of the mix as our final temperature. And we're going to be using the temperature of the water as our initial temperature. The total mass of our system is going to be the mass of the salt plus the mass of the water. We weren't given the mass of the water directly, so we're going to have to calculate that as the volume of the water times its density. And once again, we're going to be using 1 gram per milliliter for the density of the water. Finally, we'll calculate the change in enthalpy as the heat that was either released or gained by the system divided by the moles of salt. The heat will be calculated as the total mass of the system we found here times the heat capacity of 1 calorie per gram degree Celsius times the change in temperature that we calculated up here. The moles of salt will be calculated by taking the mass of the salt divided by its molecular weight. There's going to be two different salts that we're going to be using. There will be ammonium nitrate, which has a molecular weight of 80.04 grams per mole. That's going to cause an endothermic reaction that will make the temperature inside of the calorimeter go down. And then we're going to be using magnesium sulfate, which has a molecular weight of 120.37 grams per mole. This will be an exothermic reaction that will cause the temperature inside of the calorimeter to go up.
C is a little bit trickier. What we're going to do in part C, we could imagine we had that calorimeter and we have some amount of water in it, and we're going to drop in like a hot metal ball into here, okay? And it's going to come to equilibrium. All of the heat that left the metal will have gone into the water because there's no heat leaving the system. This is what we call an adiabatic system. It's all closed off. There's no heat that's able to come out. We were given the mass of the metal, the volume of the water inside of the container, the initial temperature of the metal, the initial temperature of the water, so 2 initial temperatures this time, and the final temperature that they both came to when they were allowed to come to equilibrium. So what we're going to do is we're going to use the fact that all the heat came from the metal and went into the water. Mathematically, that means that the temperature, the heat that was lost by the water plus the heat or gained by the water plus the heat that was lost by the metal is going to equal 0. Okay? Which we can express as the heat of the water is equal to the negative heat of the metal. So the metal is cooling down, the water is heating up. That's why they have opposite signs from one another. Okay? The heat of the water is going to be the mass of the water times the specific heat capacity of the water. Again, 1 calorie per gram degree Celsius times the change in temperature of the water. Okay? We're going to have to do our same trick here. We're going to take the volume of the water times its density times the specific heat capacity. We have our final temperature here and our initial temperature. We can solve all of these. Okay? We have our mass of the metal. We have the specific heat capacity of the metal. This is what we're trying to solve for, right? We have our final temperature here minus the initial temperature of the metal. If we divide by this term and divide by this term over here, we will solve for specific heat capacity of the metal, and we now have an expression where we know all of these values and can plug them in and chug out what this guy should be. Okay? So that's pretty much it. You guys should now have all the tools you need to be successful with this lab.